chances of a failure, so it doesn't become too serious. So those are the four methods of maintenance, the four maintenance philosophies, if you like, that we're going to explore this afternoon. Reactive maintenance, we wait for it to go wrong and then we fix it. Preventive maintenance, we try to estimate as best we can when it'll go wrong or when it's reached the end of its useful life, and then fix it before it reaches that point. Predictive maintenance is where we monitor its condition and then we fix it when it's necessary, when the sensors or equipment tell us that it's time to change that particular component. And then we have proactive maintenance, where we do everything we can to try to stop something going wrong, or if we can't stop it altogether, at least we try to minimize the consequences of it failing. So, as I said, those are the four basic areas of maintenance that we're going to look at this afternoon, look at the advantages and disadvantages of each. So starting with the one at the top there, reactive maintenance, we're going to use a very simple little machine to illustrate our maintenance philosophies this afternoon. It's a very simple machine with just one hydraulic actuator, and it's a device for making cakes. We have a cake mixture, some raw material coming along from the right hand side on a conveyor belt. The cylinder then extends to form the cake into its proper shape, and then it disappears off to the next process in the manufacturing process on the left hand side. I don't know if that's actually how they make cakes in practice, but it'll do to illustrate the things that we're talking about this afternoon. So we then have a hydraulic power unit over on the left-hand side, just operating the cylinder. Well, let's suppose that in the middle of our manufacturing process one day, something goes wrong with the machine. It stops working, the cylinder extends, but it doesn't retract. So we start to get alarm bells ringing, we get lights flashing to tell us something has gone wrong with the machine. And pretty quickly we started to get a buildup of raw material on the right hand side there, which extends pretty rapidly until we've got a big pile of raw cake mixture waiting to be processed. So obviously we need to do something about it. So if we analyze the process that we work through in that sort of situation, when we get an unexpected breakdown on a machine, first of all, we've got to go and locate the maintenance people. That could take a certain period of time, let's say half an hour. We then got to brief them on what the problem is. They then have to try and diagnose what the fault is. Sometimes that's easy to do. If it's a hose that's blown off or something like that, then it's pretty obvious where the fault lies, but sometimes it's a little bit more obscure. So they have to do work through some sort of diagnosis process to try and figure out, is it a mechanical fault, is it an electrical fault or a hydraulic fault? And that can take some time very often. Let's say it takes an hour and a half in our case. If they diagnose the problem as a faulty pump, the pump has failed for some reason, then they've then got to ring round different stockists, distributors, to see if they can find somebody who's got a pump in stock. That might take half an hour. And then they've got to wait until the pump is dispatched. It's probably coming express delivery, but with the best will in the world, it's going to take probably a day before it reaches us. Then we have to fit the new pump on the power unit and adjust it if it has adjustments on it. We've then got to flush the system out to make sure that all the little bits and pieces from the pump that's failed have been flushed out of the system and they're not going to do any more damage. We've then got to clean the whole place up, get rid of all the cake mixture that's lying around. So in total, we find that we've spent maybe 32 hours trying to rectify the problem. If our downtime cost is fairly modest, let's say it's something like £1,750 an hour, which is not a great deal in this day and age, then if we multiply the number of hours down by the downtime cost per hour, we find that it's cost us something like £56,000. Add on the cost of the cake mixture that we've had to scrap off because we couldn't process it. We've had to buy the new pump and pay for express shipping of it as well. So our total breakdown cost is something like £75,000. 87,500 euros or $94,400, depending on which currency you're used to. So a simple little breakdown like a failed pump can cost us quite a lot of money. And in fact, there has been some surveys done of the Fortune Global 500 manufacturing and industrial firms. These are the big boys around the world, if you like, the big manufacturing organizations, the likes of General Motors and Airbus and Hitachi and so forth. And it's been estimated that they lose something like 8% of their annual revenue due to unplanned downtime, which works out to something around about $860 billion a year. It's a very precise number. I don't know how they arrived at that, but I wouldn't argue with it. I think it's probably quite correct. Excuse me. But as we can see from our breakdown on the right-hand side there, the thing that took the longest, 24 hours, was waiting for a new pump to arrive. So we may say to ourselves, well, we can get round that problem next time by holding some spare parts for the machine. So let's fill up our spares department with spare pumps and spare valves and spare oil and electric motors and so forth. But as we all know, spares inventories tie up a lot of capital in a company. They take up a lot of space. They have to be managed. They have to be counted every time we do a stock take and so forth. And over a period of time, of course, they all deteriorate. Nothing lasts forever, even if it's just sitting on a shelf. So by the time we come to use something, we find it's gone rusty or it's past its sell-by date or whatever. And probably a lot of the equipment that we hold in stock on our shelves will never ever get used anyway. By the time the cake machine is pensioned off, we end up scrapping a lot of the stuff that we've held in the stores. So rather than being a case of just-in-time manufacturing, it's more a case of just in case. We'll hold a couple of these just in case something goes wrong, and we better hold a few of those. And it works out to be quite an expensive process. So summarizing then reactive maintenance, the advantages of it, well, if nothing fails on our machine, it's the lowest cost solution. If we're lucky and the machine carries on working satisfactorily from the day it's installed to the day it's pensioned off, then we win because it's not cost us anything in spare parts or maintenance and so forth. It's probably an acceptable approach to take if the consequences of a breakdown are relatively trivial or minimal, if you like. If you take the example of a remote control for a television set, I suspect that very few of us will take out the batteries once a week and check their voltage and put them back in again. We wait until it doesn't work anymore before we do something about it, because the consequences of our remote control not working are pretty trivial, really. We take the back off every now and again if it doesn't work, and we roll the batteries around, and then that gives us another couple of days. But eventually we have to replace the batteries. Reactive maintenance doesn't require any forward planning. There's no activity involved in advance. But looking at the disadvantages side, it can very often be the highest cost solution if something major fails. As we've seen with our cake machine, just a simple little failure cost us £75,000. So it can be the highest cost if something goes wrong dramatically. Obviously, it's not going to be an acceptable solution, if a failure of a component causes a dangerous situation. If something can fail that can injure somebody, then again, that's not really the way to go about things. Or if it can cause environmental or collateral damage, just as something as simple as a hose burst on a machine operating on a river or a canal or in a forest somewhere, can again create a lot of environmental damage if we're not careful. And of course, the first failure may cause consequential failures as well. A machine that's failed completely, catastrophically, a catastrophic pump failure or something like that, even if we've replaced the pump, There's always the danger of little bits of the old pump still floating around in the system, perhaps, which means that the new pump is not going to last as long as the original one. So we may get consequential failures as a result of the first failure. So it's not always the best thing to do, reactive maintenance. There are times when we have to use it, but it's not always the best method to use, as we've just mentioned there. So if we move on to the next philosophy, which is the preventive maintenance approach, where we're going to estimate where something will go wrong and fix it before it does. So the question we can ask ourselves is, could we have predicted the life of our pump on our power unit? If we estimate that it's going to fail somewhere around the end of April, then we can say, okay, well, in the middle of April, we'll change the pump. In April, we'll change the pump. In June, perhaps we can change the filter element because we think that's going to be clogged up around about that time. In July, we'll change the cylinder because the seals are probably going to fail sometime soon if we don't. And therefore, we've now got a much more planned approach to our maintenance. It's a routine procedure now. We can carry out maintenance at times that are convenient to us. We can do it during our annual shutdown or at weekends when we don't have to stop production. And in all likelihood, we can reduce the amount of spares that we have to carry as well, because we know what we're going to change and we know when we're going to change it. So we don't have to stock up with lots and lots of spare parts. So we've reverted back now to a just-in-time process, if you like, rather than the just-in-case situation that we had before. It's now a much more planned approach to maintenance. But the question arises, of course, is can we predict the life of components? This is some actual data that I've uncovered from a mining company which is looking at pump failures on an excavator application. So along the bottom here, we've got the life of the pump in terms of thousands of hours, and up the vertical axis, we've got the number of pump failures. As we can see at the beginning here, there are a number of pumps that died young, what we call infant mortalities, if you like. And we can put that down to probably incorrect installation of the pumps or incorrect, inadequate flushing of the system. When a pump has failed, we put a new pump on without flushing the system out properly, and therefore the new pump fails pretty quickly. So we can probably account for those, and maybe we can do something about that by educating or training our maintenance people a little bit better. So let's ignore those for now. But even then, we've got quite a large spread of pump failures or lifetimes of pumps, if you like. It's what the statisticians call a high value of sigma. So the question arises, in looking at that data there, where would we choose to replace our pump? Some pumps fail quite early, some pumps go on for quite a long time. And the choice of time along our time axis of when to replace a pump is not a difficult decision to make. If we replace our pump somewhere in that area there, then we're going to be replacing some pumps that have got maybe thousands of hours of useful life left in them. So that's an unnecessary expense, really. And of course, some pumps will have already failed by that time as well. If we carry on into this area here, then most pumps will already have failed. So we haven't achieved the objective that we're trying to. But again, some pumps will last longer. So again, it's a very difficult decision to make as to whereabouts our pump replacement should be, how long our pump is going to last. And if we think about the reason for that, what is the life of a typical pump? Well, it depends upon a number of factors. It depends upon the operating pressure of the pump and also any pressure peaks that are occurring in the system. It depends very much on the inlet conditions of the pump, whether we're cavitating the pump or drawing air into the pump inlet maybe. Depends on how fast we're driving the pump. It depends upon the very much on the contamination level of the fluid that we're using, how clean the fluid is. It depends also on the fluid temperature, and also the fluid type and the quality, whether we're using a standard mineral oil or whether it's maybe a fire resistant fluid or an ecological fluid or something like that. That again will determine or affect the pump life. Depends also on the duty cycle of the pump, how often it's on load and how often it's off load. It also depends upon how well the pump has been installed. Has the shaft been lined up correctly? Is the drain connection correct, and so forth? Also, the manufacturing quality of the pump. Obviously, some pumps will fail just due to manufacturing quality reasons. Also, the pump design. Some pumps inherently will last longer than others, and there may be other factors as well. So there are at least 10 factors that affect the life of the pump, many of which are very unpredictable. If we have no data to go on, if we have no history of pump failures and which we've recorded, then all we can do basically is to go by manufacturers' recommendations or their data, modified if necessary for the condition that our pump or conditions that our pump are working in. Maybe we have experience of similar applications as well, which we can use, or maybe we decide to strip the pump down every so often and just examine its condition. But then again, that is fraught with danger sometimes if we're stripping it down in less than ideal conditions out in the field somewhere. If we don't put it back exactly correctly, then again we can introduce faults where no faults existed before. So that is not always, again, a good thing to do. If our failure data looks more like that, however, if the value of standard deviation is much smaller and everything is grouped much closer together in terms of its failure time, then things become a little bit easier. We've got much less uncertainty now in the system. So we can say that, okay, well, let's play safe and replace our component right at the beginning here, because we're not going to lose very much even if we're wrong. So that applies to things like the fluid itself. We've got a lot of good information on how long fluids last. We've got years and years of experience of hydraulic fluids. So again, if we can accurately predict how long something is going to last, then that's not too bad a situation. Also, if the cost of the components is very small, if we're talking about filter elements and seals and air breathers and maybe hoses as well, perhaps, if they're low cost components and they're easy to change, then again, replacing them fairly early on is not too much of a problem. We're not going to lose too much money. And again, if we replace them right at the beginning of where we think they're going to start playing up, then again, we can be fairly safe that they're not going to fail unexpectedly. So there are some components, as I say, that is quite easy to change on a preventive basis. So just summarizing this process then, advantages of preventive maintenance is it's a good approach to take when we can accurately or fairly accurately predict the lifetime of components, because then we can be pretty sure that they're not going to fail unexpectedly and we're not going to replace them unnecessarily. It's also probably a good approach for low cost components, filter elements, air breathers, seals, and so forth. If it's not going to cost us very much to change a filter element, then let's do it. And again, maintenance is carried out on a planned approach, probably reducing spares inventory as well at the same time. Disadvantages, though, it can be a costly process if we underestimate component lifetimes. It can also be a costly approach if we overestimate component lifetimes. We either replace perfectly serviceable units or we don't replace them in time and they still fail unexpectedly. So again, if it's a situation where it's difficult to predict the lifetime of a component, it may not be quite so applicable. And if we start stripping units down to examine them at regular intervals, then again we run the risk of introducing faults where none existed before. So moving on to the third philosophy then, which is what we call predictive maintenance, where we monitor the condition of something and only replace it or repair it when we think it's necessary, when the monitoring or when the feedback tells us it's time. So the question arises now then is, could we have monitored the pump's performance on our power unit? It's the pump that failed, so could we do anything to monitor the situation or the condition of the pump, which would have told us in advance whether it required replacement or not? So what we need to do is to decide what aspects of the pump's performance we can monitor and which is going to give us the best indication of its condition. We need to assess what we call its performance level, and that could be the output flow that the pump is creating, because as the pump starts to wear out, the flow may very often reduce. It could be the pressure ripple that the pump is developing on the output side, on the outlet side of its, on the outlet side of the pump. It could be the temperature that it's operating at. It could be its noise level. It could be the vibration level of the pump. It could be drain line flow if it has an external drain connection. It could be the drive torque of the pump, or it could be a combination of any of those factors there. So somehow or other, we can monitor the performance level of the pump. And if you look at a lot of texts on predictive maintenance, they tend to assume that components fail following that sort of characteristic. They start off operating at a very satisfactory level, and obviously then they gradually decline, get worse and worse and worse. Well, that's not always the case of hydraulic components in my experience. It may be true of something like a gear pump, which starts off at relatively high efficiency and then gradually gets worse and worse and worse. But it's probably not the case of piston pumps and certainly vane pumps. They tend to have a different failure characteristic. For a period of time, they'll gradually decline in performance. They gradually get worn out, if you like. So you've noticed a gradual decline in performance level. But when you get to a certain point, that performance level then starts to deteriorate quite rapidly. And certainly that happens with vane pumps, and probably happens even more so with piston pumps as well. So you get a gradual decline to start with, and then a sudden acceleration in the deterioration down to a catastrophic failure. So obviously we'd like to catch the pump, we'd like to change or replace the pump, repair it maybe, ideally at this point here. That would then give us the maximum useful life out of the pump before it starts to deteriorate rapidly. So that would be the ideal point at which we would change the pump. Other components, it's even more difficult to predict their drop-off in performance level or their characteristic performance level. Take something like a hydraulic hose, for example. Its performance may stay perfectly adequate for months and sometimes years. You will notice no drop-off in its performance whatsoever. It just continues to pass the fluid as it's always done. And then one day it suddenly bursts. So you then get an almost instantaneous drop off in performance as the hose bursts, and it's reached the end of its useful life, obviously failed catastrophically, and probably pumped oil all over the floor or over the field or wherever it happens to be. So that is a bit more of a tricky situation. How do we monitor the performance of something that doesn't really deteriorate until it fails completely? In many situations, we may have to resort to the good old Mark I eyeball and just do a visual check on hoses to check that they aren't cracked or they haven't been chafing against some other component or they're not bulging from the cover and so forth. There is one manufacturer that's actually developed a method of assessing hose performance, but it doesn't appear to be a commercial proposition at the moment. but one day it may be. So with things like hoses, which don't really significantly deteriorate until they fail, then we may have to resort again to just a preventive maintenance approach and say that every year or every 3 years or every 5 years, whatever, we'll change the hoses as a precaution, because that's what we estimate their useful life to be. So if you look at what we can actually monitor these days with sensors and so forth, there's lots of different properties now, apart from all the mechanical properties of force, torque, speed, and so forth, and the hydraulic properties of our system, the pressure, the flow rate, the temperature, contamination levels, and so forth, plus the electronic electronic components of our system. Solenoid valves and so forth. We can monitor voltage levels and current flows. We can monitor pump displacement very often, fluid level in the reservoir. Vibration, as we'll see in a moment, is a very useful thing to monitor. Possibly hose condition when it becomes economically viable to do that. And also we can monitor the debris in the fluid as we do in many aircraft systems. And there are lots and lots of different sensors and instruments available to us these days at very modest cost compared to what they were a few years ago. In this digital age, we can connect them up via SCADA or CAN bus or whatever. So the interconnection becomes very simple as well and cost effective. And it's the same situation that we had in our cars, if you remember it, or if you can go back as far as I can. When I started work, I used to drive to work in a car that gave me 4 bits of information. I had a fuel gauge to tell me how much petrol I had in the tank, a mileometer here to tell me how far the car had been driven, a little red light to tell me that the battery was charging or not, and then a needle to tell me roughly how fast I was going. But the needle always used to bob around a bit, so it was a mental calculation to do an average of the maximum and minimum levels. These days, things are different. You've got all the information you could possibly wish for on the dashboard of your car. Not only how fast you're going, how much fuel you've got, what time you're going to reach your destination, whether the kids have got their seat belts done up and this sort of thing. And probably in your car, you've got maybe over 100 different sensors these days, all sensing all sorts of information. You've even got one here that tells you that you've probably had a bit too much to drink and you shouldn't really be driving at all. At least I think that's what it means. So predictive maintenance, then summarizing here, we can now continuously monitor the health of our system and the system components, and hopefully then that will give us then an indication of what we call the remaining useful life, RUL, of our components. We can probably reduce the spares inventory as well. We don't have to carry lots and lots of spares. And we can justify the expense of buying a new pump with hard evidence. If we go to the accountant and say, look, the sensor tells us that the pump is about to fail, therefore we need to spend X thousand pounds on a new pump, then we can now justify that with some hard evidence. Obviously, on the disadvantage side, though, there is an additional cost. There's no getting away from it. Sensors don't come free. We have to pay for them, but they're not huge amounts of money these days, as we said. And the connection to some sort of central point again is much easier now than it used to be. It also requires, however, some know-how to be able to interpret the data that the sensors are giving us and know what to do as a result, which again we'll talk about in a moment. It's probably interesting to observe that even on something as mundane as a remote control for our television, it's now giving us a warning that our batteries are running out. On my remote control, it flashes up a warning on the television screen telling me to replace the batteries when they're getting low on voltage. So it's even possible to do it on something like that. That is, strictly speaking, something we call condition-based monitoring. It's telling us the current state of something rather than predicting how much useful life it has left. And then finally, proactive maintenance. How do we try to stop it going wrong or to minimize the consequences of a failure? Well, if we look at our power unit that we had operating our cake machine, We can look at it and say, well, what could go wrong with it? We know the pump can fail, but we could get contaminated fluid or moisture in the fluid. That's a possibility. It could start overheating if we're not careful. We can get a hose failure, obviously. Um, we can get seal failures within the cylinder and within some of the valves as well. Coils could burn out on our solenoid valves. All the adjustable components could be incorrectly set, or they could vibrate loose. The pump could fail, as we know, as could the electric motor, and somebody could put the wrong sort of fluid in the tank. So there are all sorts of things that could go wrong with it, including the low fluid level there caused by a leakage. So we can carry out what is known as a failure mode and effects analysis, either at the design stage of our system or at some stage where we want to improve it maybe. And that FMEA results in something called a risk priority number, which is a combination of the severity of the failure, the probability that will happen, and something called undetectability. I'm not sure if that's actually a word, but what we mean is how easy or how difficult is it to assess the condition of a particular component. So we could then say, okay, well, let's redesign our power unit to make it much more reliable. We'll provide it with a positive head reservoir to give the pump the best inlet conditions that we can. We'll put a drain on the tank so we can drain out fluid, drain out water that collects at the bottom or heavy contamination. We can color code the tank or the fluid filling point to make sure we don't put the wrong sort of fluid in there. We'll fit a filter on the filling point to make sure we filter the fluid before it gets into the tank. Fluid level sensors indicating breathers, drying the air as it's drawn into the tank. We can put a cooler on there should we get an overheating situation. Put an offline filtration unit on to keep the oil as clean as we can. We can put a sensor on there to assess the fluid condition and temperature. Pressure test point, so we can set valves to the correct pressure setting and so forth. Hose burst valves and restraints, prevent any whiplash problems. Flow meters to check the pump flow. Shut off valves that are monitored to make sure we can't start up the pumps with the inlet and drain valves closed. Put on a complete standby pump set if necessary. Vibration sensors, lockable adjustments, and so forth. So you're probably looking at that and saying, well, that's going to cost quite a lot more money. And you're absolutely right. It will cost more money, but maybe not the £75,000 that our first breakdown cost us. And we may not have to go to that full extent every time, but those are the sort of things that we can think about to try and prevent failures from occurring. So summarizing that, proactive maintenance can, as a byproduct, prolong the service life of the system because we're giving it the best conditions that it possibly can to work under. It aims to eliminate the costs and consequences of unseen breakdowns, simplifies troubleshooting if breakdowns do occur because we've got a lot more information about the system. But it does require quite a detailed analysis of the system right at the very beginning. There is some additional cost penalty involved, as of course every sensor costs us a bit more money, but as we said, they've become much more cost effective in recent years. And people sometimes ask, well, is it really possible to prevent something going wrong? Is proactive maintenance possible? Well, some of you may recognize that it's one of the most famous bridges across the River Thames in London. It was the first bridge that you came to as you travelled up the Thames estuary from the North Sea, and in the 19th century when it was built, it had to open up to allow the tall-masted ships to pass through to the Port of London. Port of London was the biggest port in the world at that time. So since every ship had a tall mast on it, the bridge had to open. And the 1,200-ton bascules, as they're called, on either side were lifted and lowered by means of a hydraulic system consisting of 8 90-litre per rev hydraulic motors operating on a curved rack and pinion arrangement. The bascules were also counterweighted as well, counterbalanced, so that the forces involved weren't too great. Well, Tower Bridge opened on the 3rd of June 1894, and its first failure was on the 1st of July 1968, over 74 years later. And during that time, it had opened and closed over 350,000 times successfully. So it wasn't possible to prevent a complete, it wasn't possible to get perfect reliability. It did eventually fail, but 74 years of satisfactory operation is not a bad record. These days, we aim for something called 6 Sigma reliability, which allows us 1 failure for every 300,000 opportunities. And as you can see, the Victorian engineers achieved that 130 years ago. So it may not be possible to prevent something failing completely, but we should be able to get pretty close to it these days. So those are the 4 philosophies of maintenance, if you like. They're not mutually exclusive. There's no reason why we can't combine them together. If we can stop something going wrong, then all well and good. But if we can't, we ask ourselves, can we monitor its condition? If we can't do that, can we predict when it will fail? And if we can't do that, then all we've got to do then is basically stock up with some spare parts and make sure that our maintenance people are well trained to spot any problems and know the procedures for replacing components. Something like a solenoid, for example, on a solenoid valve, you can't stop it going wrong. You wouldn't be able to monitor its condition. You can't predict when it's going to fail. So all you can do with things like solenoids is make sure you've got a couple of spare parts on the shelf ready for when they're needed. So just to finish off then with another example of a hydraulically operated conveyor conveying rock or soil or whatever to a certain part of our system. If we set the device in motion, as the hydraulic motor rotates, the conveyor belt distributes our material where it's supposed to. But then how are we going to monitor the condition of our motor driving the conveyor? We can monitor probably its speed quite easily. Most motors will have the option for a speed sensor that can be built into them. We can monitor the flow rate that's feeding the motor. Probably the forward flow rate is all we need to monitor. The reverse is only very seldomly used, just for relieving jams and so forth. And if we know the displacement of the motor, then we've got all the information we need to be able to assess its condition. The flow monitor will probably give us a signal for pressure and temperature as well, as a byproduct. So if we're trying to assess the volumetric efficiency of the motor, if that's our performance criteria, if you like, that is defined as the actual speed divided by the theoretical speed. The theoretical speed is the flow rate divided by the displacement. So if we know the displacement, we know the flow rate, and we know the speed, we can then work out quite easily the volumetric efficiency of the motor. And what we'd expect to see is a gradual decline in volumetric efficiency over months and years, perhaps, as the motor gradually wears out. It's never going to start at 100%. It may start at 95, something like that. But then there will be a gradual drop off in efficiency as the motor wears. It probably wouldn't be a nice straight line like that. It would be a bit more of a lumpy characteristic due to variations in flow and pressure and so on. But we can set a minimum level. We can say that when the efficiency has dropped to this particular level, 75% or something like that, that's the time that we can replace the motor. At the other end of the system, where the pump is creating the flow and the pressure to drive the motor, then we've got a few more variables to consider now. The pump may well be a variable displacement pump, so we need to monitor the pump's displacement. That again is a standard option usually, as is the speed of the pump. If we don't have a speed from the engine that's driving it, we can monitor the pump speed again quite easily. We can assess the pump flow rate with a flow monitor on its output, usually measuring pressure and temperature as well. Vibration is also a very good indicator of pump condition. not only if we're looking at the state of the pump bearings, but if we have an axial vibration sensor on the pump here, that's also going to tell us the state of the shoe and the piston connection here. As the shoe and the piston connection starts to wear, we get an increase in vibration along the axial part of the pump, and therefore we can spot that quite easily using a vibration sensor and get a reasonable amount of warning then as to when the pump is going to require replacing. We can probably get 2 or 3 days or even a couple of weeks warning now with when we reach this sort of point here. Again, vibration sensors don't necessarily have to be permanently connected. If we do it at regular intervals, we can use a portable vibration sensor these days. Very cost effective. We can also monitor the pump inlet pressure as well as the vibration. We might as well monitor the fluid condition as well, and then feed that back, all that information back to our hydraulic specialist, who then analyzes all that information and makes a decision as to when to replace the pump. Except it's not a particularly easy task to do unless you're very skilled in this process. So increasingly these days we're going to be using artificial intelligence to do that analysis for us. It looks a bit like a jellyfish in a tank, but it's meant to represent artificial intelligence, or machine learning, as we call this application. So that can now assess all the inputs. We might as well take all the inputs from our system into our machine learning algorithms, and then they can assess for us what sort of state that system is in. We're probably still going to need some supervisory intelligence to look after this. Computer-based systems are still not 100% perfect, as Boeing found out a few years ago with their MCAS system, as the Post Office in the UK is finding out at the moment. So all you hydraulic specialists out there, there's still going to be a job for you, I think, both in the programming of the artificial intelligence and also in supervising it as well. But it can also go one step further and actually give us a remedy for the situation as well. If it decides that our pump is wearing out a bit too quickly, it may say, well, the reason for that is your oil's too dirty from our oil sensing device. So then it produces a remedy for us as well. Start to look at the filtration on the system. So then that becomes what we call prescriptive maintenance as well, which is one step further than proactive maintenance. So what we can now do, as I say, is we can do a complete mix and match on our maintenance philosophies. If we look at the complete system for our conveyor, we can use both preventive, predictive and proactive techniques, depending on which is the most suitable for each particular component. We built a standby system in here, which is proactive. We've got monitoring equipment in there, which is predictive, and we're using preventive maintenance approach on things like hoses and so on. And it obviously depends upon what it is, what particular activity we're involved in. If we're looking at maintaining a remote control for a television, then we can be down here somewhere in terms of our maintenance approach. If it's a nuclear power station that we're looking after, then again we probably need to be up here somewhere. But again, there's no reason why we have to use one or the other of these approaches. We can say mix and match them, use whichever is the most appropriate for whichever component whichever system we're looking at. Very quickly then, I'll just summarize what we've talked about. Reactive maintenance, looking at waiting until something goes wrong before we fix it. So only when it goes wrong do we start watering our plant. But it doesn't always get fixed back to its original condition. Preventive maintenance, we try to estimate when it will go wrong and fix it before it does. So we'll decide to water our plant every Tuesday. But if the whole week has been full of baking hot sunshine, then by the time Tuesday comes round, it may be too late. Our plant has failed already. On the other hand, if you're in the UK, it may have been raining every day since last Tuesday, so there's no reason why we need to maintain it at all. If we dig it up every Tuesday and check its roots, then we're probably doing more damage than we're solving. If we use predictive maintenance, we can then monitor the condition of our plant, its temperature, its heartbeat, its moisture level, and so forth, and its growth, and then predict exactly when it's going to require maintenance. And if we use the proactive approach, then we're going to try and do everything that we possibly can to stop it going wrong, to stop it dying off, killing all the bugs, stopping all the pests, giving it ideal conditions to grow under as well. So there we are, the 4 philosophies of hydraulic system maintenance. If you want to read more about it, Webtec have published a book on the subject, available from Amazon, either as a paperback book or a Kindle edition, whichever you prefer. You're a bit late now for a Valentine's Day present, I'm afraid, but Mother's Day is coming round, so it makes an ideal Mother's Day present, should you wish. Okay, Sam, so that's me done, I think. Do we have any questions?
Thanks, Steve. Brilliant. That was excellent. Thank you very much. There was one. Let me scroll up. There was one from Tommy Wheeler from Cramp. Hi, Steve. And which company and what technology were you describing for testing hydraulic hose performance?
It was the company that I worked for a number of years. It was actually Aeroquip that came out with something called a LifeSense system for hoses, where you could, they're a little bit secretive about it, how it worked, but you could then build in a sensing device that would sense the condition of the hose and then feed that back via a digital electronic link. When I looked at that when I was preparing this presentation, it seems to have disappeared from their catalogue. Quite why, I don't know. It may be a commercial decision, it may be a cost decision, and so forth. But certainly the technology seems to exist, but it's not. I'm not quite sure whether it's a commercial proposition at the moment.
Okay, thank you. There's no other questions in the chat unless there's anyone else that has anything they'd like to ask now. By all means, unmute yourself and ask the question. But if not, that's not a problem. I'm just gonna, while we wait, I'm just gonna steal the screen, Steve. Just this up. Hopefully this is. So yeah, just I say by all means, ask a question now if you have one. If not, then this will be, you'll receive 2 emails after this. One will be the recording. You might notice I missed the first minute of the recording, but that was a slight miss. I didn't press the right button. And you will then get an email from me, from marketing@webtec.com, which will have the links that I've put in the chat for a white paper and the survey. As I say, feel free to download white paper, have a look, a read. I think it's very useful. And if you have a few minutes to please fill in the survey, that would be excellent. Just the last minute, I mean, so our sort of idea for this year is to run 4 webinars. We've done 2 already, and the other one is on the website. I can point you to that as well. And we're looking at doing another 2 this year, as we continue to just try and provide as much useful information as we can for you all in hydraulic maintenance and all manner of other things. So you'll find out. I shall share all the information as I have done with this one, and hopefully to see you again in the next webinars coming up. So unless there's anything else, we'll end it there. So thank you again, Steve. I think that's the second time I've heard that, and it's still very interesting. So thank you for your time.
Thank you, Steve. Thank you, Sam.
Great.
And I'll thank everyone for attending, and hopefully see you again soon.
Thank you.
Thanks, everyone.